started.
So for number 1, this is a 2 by 2 matrix. Now remember, the straight lines on the sides are telling us that we're finding a determinant here. So we go ahead and do that. It's a down diagonal product, which is the -6 times 3, which makes -18. Then the up diagonal product, which is 8 times 1, which is 8. The determinant is the down diagonal minus the up diagonal. -18 minus 8 is a -26. That's our determinant there. For number 2, I specified the diagonal method, which means we rewrite first 2 columns. And then we're just going to do the diagonals. So 5 times 2 times, or 5 times -2 times 5 is a -50. Plus 2 times 3 times 1 is 6. Plus -7 times 3 times 2 is a -42. Which I believe makes -86. Is the total down diagonal. Going up, we have 1 times -2 times -7 is 14. Plus 2 times 3 times 5 is 30. Plus 5 times 3 times 2 is also 30. That's a positive 74. So this determinant is -86 is my down diagonal products, minus the up diagonal products is positive 74. That is a -160 is that determinant. Number 3, I ask you to do it using partial expansion, using our minors. I am going to pick this column to expand about. I could have also picked that second row because both of them have a 0 in it, but I'd rather work with 5 and 1 than work with 6 and 8. So I'm going to expand about that column. We should get the same answer no matter what row or column you chose to expand about. So first we're going to find the cofactor. So the entry here is 5. It's in row 1, column 2, which adds up to 3. So that's an odd entry. So it's -1 times 5 gives us a cofactor of a -5. The minor. Cross out that row and column. It's 6844. 6 times 4 is 24. 4 times 8 is 32. 24 minus 32 is a -8. That is the determinant of my minor. I multiply -5 times -8, I get a positive 40 as my partial. I don't need to do the 0 because the 0 is going to have a cofactor of 0, so it doesn't matter what the determinant of the minor is. I'm multiplying it by 0, so that would be 0. I'm going to jump down to the 1. For the 1, that is in row 3, column 2. That adds up to 5. That is also an odd number. So its cofactor is -1 times the entry of 1, giving me a -1 for cofactor. Its minor, I cross out its row and its column. The minor would be 4, 5, 6, 8. Do my determinant. 4 times 8 is 32. 6 times 5 is 30. 32 minus 30 equals 2. That's the determinant of my minor. -1 times 2 is a -2. We add that up, we get 38 is our determinant for that matrix. Any questions? Now, as we said yesterday, for these matrices, for the 2 by 2 matrix, this is the only way to find its determinant, is to do that crisscross, down diagonal minus up diagonal. For the 3 by 3 matrix, really doesn't matter. We could use the diagonal method or we could use the expansion, the partial expansion. We'll get the same answer. And we can always use either method with any 3x3 matrix. The main reason I show you the partial expansion here is because for any matrix larger than 3x3, that is the only way we can do it. We have to expand it into partials. For extra credit, it's posted in next week's folder out there on Blackboard. I did post a 5x5 matrix that you can find the determinant of. It takes a while, but you'll be able to do it for up to 20 points extra credit, and that'll just be added onto your total. So those points are out there for you if you want to give that a shot. So the question we want to answer today is why? Why did I make you spend 2 hours of class calculating determinants and dealing with matrices, finding partials, the cofactors, the minors, all that? Why did we spend 2 hours on that? Well, because there's something called Cramer's rule. Now, it actually depends on what textbook you're looking at. Some textbooks actually spell it with a C rather than a K. I'm really not sure which one is correct or not, but I've seen it both ways. What Cramer's rule says is we can use these matrices and their determinants to solve a system of equations. So the big thing is, how do we turn the system of equations into the matrices that we need to solve them? So let's set up a system here. So here's our system. 2x minus 3y equals 1, and 3x plus y equals 18. We have a system of equations. Notice that just like when we did the addition method, we're lined up, and we have to be this way. X's, y's, equals, and the constants. We have to be lined up that way, or this will not work. So I'm going to label this. That's the X column, the Y column, and the constant column of numbers. Cramer defined 3 matrices for this type of equation. There'll be a fourth one when we have 3 variables. First one is a base matrix that is just labeled M. The base matrix M consists of the X and Y columns of coefficients. So we drop the variables and we just keep the numbers. So the X column here would be 2 and 3. The Y column would be -3 and 1. That's just a Y there, but remember that's implied a 1 there. So there is the base matrix. Cramer then also defined an X matrix, noted by M with a little X by it. In the X matrix, we replace the X column with the constants. So instead of the X coefficients, it's the constants and then the Y coefficients. So notice here it was XY, here it's C and then Y. We replace the X coefficients with the constants. So the constants here are 1 and 18. The Y coefficients are -3 and 1 again. And then Cramer also defined a Y matrix, denoted as M with a little Y by it. In the Y matrix, we go back to the base matrix X and Y, and we replace the Y column with the constants. So the X column is back to being the 2 and the 3. And the second column is the 1 and 18. So these are the matrices that describe this system of equations and their solution. Well, how do we get to the solution? Well, step one, obviously, is to create the matrices. Step two is to find their determinants. You knew that had to be coming because you spent so much time on determinants. So let's do step two. Let's find their determinants. Well, 2 times 1 is 2. 3 times negative 3 is negative 9. 2 minus the negative 9 is 11. So 11 is the determinant of our base matrix. For the X matrix, 1 times 1 is 1. 18 times negative 3 is a negative 54. So 1 minus a negative 54 is 55. 55 is the determinant of our X matrix. For Y, we have 2 times 18 is 36. 3 times 1 is 3. 36 minus 3 is 33. 33 is the determinant of our Y matrix. That's step 2. Step 3 is to find the solutions. The solution for X will be the determinant of the X matrix divided by the determinant of the base matrix. And the determinant for Y, or the solution for Y, will be the determinant of the Y matrix divided by the determinant of the base matrix. So 11 is the determinant of our base matrix. The determinant of our X matrix is 55, so 55 divided by 11, you get X equals 5. For Y, the determinant of the Y matrix is 33, divided by the determinant of the base matrix of 11, we get Y equals 3. Our solution here, X is 5 when Y is 3. Pretty slick, actually. Let's do one more example, then I'll have you try one. So we're going to solve this system here. Do 3x plus 4y equals 6. And 2x plus y equals negative 1. So we're going to go ahead and pick this apart. It is, first of all, in the correct form, x's, y's, equals, and constants. So let's define our matrices. Our base matrix, remember that's the x and the y column of coefficients. The x's are just 3, 2. The y's are 4 and 1. Let's find its determinant while we're here. 3 times 1 is 3. 2 times 4 is 8. 3 minus 8 is a negative 5, is our base matrix. Let's find our X matrix. Remember, in the X matrix, we replace the X column with our constants. So that'll be 6 and negative 1. Our Y column is still 4, 1. And let's find its determinant. 6 times 1 is 6. Negative 1 times 4 is a negative 4. 6 minus negative 4 is positive 10. Next, let's find our Y matrix. Remember, in the Y matrix, the X column is back where it belongs. We replace the Y column with the constants. So the X column is 3, 2 again, and the Y column is our constants of 6, negative 1. So we do 3 times negative 1 is negative 3. 2 times 6 is 12. Negative 3 minus 12 is a negative 15. So then, X is the determinant of the X matrix, 10, divided by the determinant of the base matrix, negative 5. That makes X negative 2. Y is the determinant of the Y matrix, negative 15. over the determinant of the base matrix, which is still negative 5. Negative 15 divided by negative 5 is a positive 3. So the solution here, x is negative 2, when y is 3. I'm going to have you try one. So 3x plus 2y equals 0. And 5x minus 3y equals 19. So use Cramer's rule to find the solution to that. We'll go over it in just a couple minutes. I see the heads coming up from the paper, so let's take a look at this and see how you're doing. So let's define our base matrix. It's the x and y constants. So it's going to be the x constants of 3 and 5, and the y constants of 2 and negative 3. So we do the determinant. 3 times negative 3 is negative 9. 5 times 2 is 10. Negative 9 minus 10 is a negative 19. Is the determinant of our base matrix. For our x matrix, remember we replace the x column with the constants. That's going to become 0, 19 now. The y column is still 2, negative 3. We're going to do our determinant. 0 times negative 3 is 0. 2 times 19 is 38. 0 minus 38 is a negative 38. And for the y matrix, now the x column is back. We're replacing the y column with the constants. So the x column is 3, 5. Constants are 0, 19. We've got 3 times 19 is 57. 5 times 0 is 0. 57 minus 0 is 57, is the determinant of our y matrix. So x is the determinant of the x matrix, negative 38, over the determinant of the base matrix, negative 19, equals 2 for x. Y is the determinant of the y matrix, 57, over the determinant of the base matrix, negative 19, which is negative 3. So we have x is 2 and y is negative 3. So what happens when we run into so 3x equals 2y minus 4. And 3y equals 4x plus 4. Oops, sorry, 4x plus 7, that should be. These equations are not in the form we want them. We want them in standard form, x, y equals constants. These are not there. This first equation, 3x equals 2y minus 4, I have to get the 2y over to the left side. So I'm going to subtract 2y. So I now have 3x minus 2y equals negative 4. That is in the correct form. This other equation here, 3y equals 4x plus 7, I have to get the 4x over to the left side. Now technically that's going to be 3y minus 4x equals 7. I'm going to rearrange it. I'm going to put the negative 4x first, and then the plus 3y equals 7. Now that one is in proper form. So the solution the system we're really solving here is 3x minus 2y equals negative 4, and negative 4x plus 3y equals 7. So our base matrix x and y coefficients. For x, we have 3 and negative 4. For y, we have negative 2 and 3. We'll find our determinant. 3 times 3 is 9. Negative 4 times negative 2 is 8, positive 8. 9 minus 8 is 1. So 1 is the determinant of our base matrix. Our x matrix. We replace the x column with the constants. Still have the y column. So our constants are negative 4 and 7. Y is negative 2 and 3. We do our diagonal. Negative 4 times 3 is a negative 12. 7 times negative 2 is a negative 14. Negative 12 minus a negative 14 is a positive 2. That's the determinant of our x matrix. For y, the x column is back. This time we've replaced the y column with the constants. So the x column is still 3, negative 4. Constants is negative 4 and 7. So doing our determinant, 3 times 7 is 21. Negative 4 times negative 4 is 16. 21 minus 16 is 5. 5 is the determinant of the y matrix. So x is 2 divided by 1, which is just 2. And y is 5 divided by 1, just 5. Our solution here, x is 2 and y is 5. Well, that's all wonderful for two variable systems. What if there's a third variable? What if we have 3x plus 2y plus z equals 8 x plus 3y minus 2z equals 19, and 2x minus y minus 3z equals 13. Well, this is still in that proper form, x's, y's. Now we also have the z's, and then equals the constants. Our base matrix now will be the x's, y's, and the z's. The x's are 3, 1, 2, y is 2, 3, negative 1, and z is 1, negative 2, negative 3. And we're going to find its determinant, so let's go ahead and do it now. I'm going to use the diagonal method, so I'm just going to rewrite the first two columns. Going down, we have 3 times negative 3 is a negative 27, plus 2 times negative 2 times 2 is a negative 8, plus 1 times negative 1 is a negative 1. That is a negative 36. Is my down diagonal product. Going up, 2 times 3 times 1 is 6, plus negative 1 times negative 2 times 3 is a 6, plus negative 3 times 1 times 2 is a negative 6. I get 6 is my up diagonal product, giving me negative 36 minus 6 is a negative 42, is the determinant of my base matrix. My X matrix. Once again, the X column is replaced with the constants. I still have the Y's and the Z's. So my constants are 8, 19, and 13. X is 2, 3, and negative 1. Z is 1, negative 2, and negative 3. I rewrite my first two columns. 8, 19, 13, and 2, 3, negative 1. And let's do our diagonals. 8 times 3 times negative 3 is a negative 72. 2 times negative 2 times 13 is a negative 52. And 1 times 1 times 19 times negative 1 is a negative 19. Which comes out to be negative 143, I believe, is our down diagonal product. Going up, 13 times 3 times 1 is 39, plus negative 1 times negative 2 times 8 is a positive 16, and negative 3 times 19 times 2 is, I believe it's a negative 114. Yes, and that adds up to negative 59. So we have a negative 143 minus a negative 59. What's that coming out to be? I'm thinking I missed something there. Oh, that looks right. Did I add it all up correctly? Okay, so that it comes out to be, it's going to be plus. The 59 is 84. Does that look right? I believe so. That's a negative 84. So then our Y matrix, we put the X back in, we replace the Y column with the constants. So we have 3, 1, and 2 again for X. We have 8, 19, and 13 for the constants, and 1, -2, and -3 for z. We'll rewrite our columns. We got 3, 1, and 2, 8, 19, and 13. Do our diagonals. 3 times 19 times -3 was a -171 plus 8 times -2 times 2 is a -32 plus 1 times 1 times 13 is 13. So that is, I believe, a -190. Downs. Going up. 2 times 19 times 1 is 38, plus 13 times -2 times 3, I believe it's a -78, plus -3 times 1 times 8 is a -24. I believe that comes out to be a -64. So our determinant here, -190 minus a -64, which is -190 plus a +64, which is a -126. My Z matrix. Oh, you probably predicted it by now. My X and Y columns are back where they belong. We replace the Z column with the constants. So X is 3, 1, 2. Y is 2, 3, -1. And Z is 8, 19, 13. And I rewrite my first two columns again. I'll do my diagonals. 3 times 3 times 13, I believe, is 117. 2 times 19 times 2, I believe, is 76. 8 times 1 is 8. No negatives here? Be a -1 on the bottom there. There's a -1 here. So this would be a -1. This would actually be a -8. So that adds up to, what, 195, I believe? No, 185. $185 is what that adds up to. Our up diagonals. 2 times 3 times 6 is 48. Plus -1 times 19 times 3 is a -57. Plus 13 times 1 times 2 is 26. That's going to come out to be, oh, what, -9, be a +17, I believe, for the up diagonal total. Yep, that looks correct. So we do our down diagonal, 185, minus our up diagonal, 17, which gives us 168. Is that determinant? So now, X is the determinant of the X matrix, -84, over the determinant of the base matrix of, where is it, -42. That's a +2. Y is the determinant of the Y matrix, -126, over the determinant of the base matrix, -42, which is a +3. And Z is the determinant of the Z matrix, 168, over the determinant of the base matrix, -42, which is a -4, giving us a solution X is 2 and Y is 3 and Z is -4. We will look more at the 3 variable systems in Cramer's rule tomorrow. For now, your homework, there's a worksheet posted in Blackboard. I just want you to do the 2 variable systems for now. If you want to venture ahead into some of the 3 variable systems, you're welcome to. We will look at those more tomorrow, like I said. Anybody have any questions? Okay, so we have about 7 minutes left. If you'd like to get started, you're welcome to. I'll be on the network here to answer any questions.